And this is Mr. N. Jaidass, Annamacharya Institute of Technology and Sciences, Tirupati, Department of HNS. Under the applied physics, we are discussing. Now we are going to be discuss the topic semiconductor. Now, what is semiconductor and what is the characterization? All these things we are discussing in a detailed way. It is under fourth unit. So see the data. What is semiconductor? We are going to be discuss. A semiconductor is a substance whose conductivity or the resistivity lies in between of conductors and as well as insulators. So what is conductors? See we are examples also given. Silicon is a semiconductor. Next one, germanium is a semiconductor. This is gallium arsenic. This also semiconductor. So these are the semiconductors. And another one is you go for the properties of semiconductor. We are going to be see. What is the properties of semiconductor? They have a crystalline structure. See, you know what is amorphous and what is crystal. Crystal is a three-dimensional, a regular arrangement array. So the atoms are in three planes. There is a regular arrangement. So therefore, you go for these things. The next one, they have formed by covalent bonds. You know the chemical bonds, that is ionic bond, covalent bond. But covalent bond is the sharing of electrons. So in the case of silicon and germanium, whatever the semiconductors, it form covalent bonds. So this is called. Next third point, they have negative temperature coefficient of resistance. And you know at temperature 0 Kelvin, they behave as insulators. And higher temperature it becomes a conductors. So this is depending upon the temperature phenomena. We can see the next house. When the impurities, that is fourth group impurities or fifth group impurities is added, then the pure semiconductor, its electrical conductivity increases. That is very, very important. If we add some impurities, whether it is the third group elements or fifth group elements, then what happens? The conductivity of semiconductors is increases. Okay. Next one. Based on the purity, semiconductor further classified into two types. That is number one, intrinsic semiconductors, and number two, extrinsic semiconductors. Then what is intrinsic semiconductor? How you define semiconductor intrinsic? A semiconductor is an extremely pure is known as intrinsic semiconductor. So if it is available in nature, the pure semiconductor, that is, we can say silicon or your germanium, etc. Then see consider a pure semiconductor like silicon or germanium crystals. We know that germanium is a fourth group element, yes, and it has four valency. Whenever you can say fourth group or fifth group, it has some valency electrons. So in the case of germanium, it has fourth group element. To get stability of silicon atom, will make four covalent bonds with the neighboring silicon atoms only. So silicon is form covalent bonds with another neighboring silicon atoms. And because of the temperature, these are depending different based on the temperature. You know already. We can discuss at 0 temperature Kelvin or greater than 0 Kelvin. What happens? You know at 0 Kelvin, all are as a insulators. See at absolute temperature 0 Kelvin, at absolute temperature 0 Kelvin, all the electrons are tightly bounded by the semiconductor atoms. In the inner orbital, electrons are bound to the nucleus, whereas the valency electrons are engaged with covalent bonding. Okay, at this temperature, the covalent bonds are very strong, and there is no free electrons. Therefore, the semiconductor crystal behaves as a perfect insulator at absolute temperature. That means what we can say absolute temperature is 0 Kelvin temperature. So at 0 Kelvin temperature, is silicon or your germanium acts as a insulator only. Then at a higher temperature, what happens? You see the second one. when the temperature is raised, some of the covalent bond is semiconductor broke due to the thermal energy. That means if you give some thermal energy, that means some temperature, then what happens? The one of the covalent bond will broken. The breaking of covalent set whose electron free, at the same time the vacant site produces covalent bond called hole. That means one hole is created in a semiconductor. A new topic, that is hole, is created. The result is that a few free electrons exist in semiconductor. These electrons can constitute a tiny electric current. If the potential difference E is applied across the semiconductor, you see the diagram. See, we can given here. See the semiconductor. See, this is the, what we can say, this is the structure of your semiconductor. You are now using germanium. See, this is one covalent bond, another covalent bond, another covalent bond. Therefore, 4 electrons of valency electrons having 4 covalent band with neighboring of your germanium atoms. So, how the energy levels are seen, very, very important. This is your valency band area, and this is your conduction band. In between, there is a Fermi energy level, EF, we can notate here. So, in between, the energy gap is approximately in semiconductors, that is what 1.1 electron volts. Okay. In the valency band only, electrons are there at general temperature 0 Kelvin. You can't find even single electron in the conduction band. What happens? Because it is at 0 Kelvin. So therefore, at 0 Kelvin, what happens? No electrons are there. This is a 0 Kelvin phenomenon data. And at the higher temperature, the one of the covalent bond is broken. Therefore, what happens? One hole is created. So that we can see now. This is the higher temperature phenomenon. At higher temperature, what happens? The covalent bond is there, but one of the covalent bond, this is the broken bondage, and because the only single electron, this electron is created. So therefore, at higher temperature, one electron is available. See here in the energy levels also, these are electrons, and here there is some see, if some electrons are moved from conduction band. This is a conduction band area. So therefore, now what we can understand, some electrons is available at conduction band. So instead of conduction, in the conduction band, the electrons are moved from valency band to conduction band. So therefore, what happens here? We can see the holes are formed. So therefore, in the conduction band, now the conduction band electrons are available. Okay. And now we go for another one. Based on the purity, you know extrinsic and intrinsic. Now you go for extrinsic semiconductor. What is extrinsic and what is intrinsic? You know. See the energy levels of the electrons based. The electrical conductivity of pure semiconductors is very small. To increase the conductivity, impures are added. This impurities added semiconductor is called extrinsic semiconductor. Okay, see the diagram. This is okay. Now you go for see. And another definition is there. The conductivity of the intrinsic semiconductor in between the a small amount. So we are adding whether the third group element here or the fifth group element here. It is what we can say the impurities. So these impurities are called extrinsic semiconductors. Based on the this is our what we can say the N-type semiconductor based on the impurities adding N-type semiconductor and P-type semiconductor. See next one. What is N-type semiconductor? When a small quantity of pentavalent impurity is added, that is very, very important. The pentavalent, that means in outermost shell we have 5 valences. That is you are whatever you want adding the pentavalent in the fifth group element, you can get pentavalent elements. So if you add this one, then you see the structure of germanium. Once again, you are adding the arsenide, and because of the arsenide dopant, whatever one extra electron is there, extra electron is available. These extra electron we can say free electrons. See the energy diagrams also. These are the donors level, And from this high temperature, all the donor level electrons are moved to conduction band. Now in the conduction band, we can get the free electrons. So it is impossible by doping the pentavalent. You go for another one. What is p-type you want to see? What is p-type? If third group element is there, like your boron or aluminum, we can get only 3 electrons. Because of 3 electrons, this is 1 electron, another one is the 1 electron. These are, and then one fourth electron is not available. Because of that, one hole is created. So because of the hole is created means this hole can able to that accept the electrons. So these are acting as acceptors. Okay. Now what is the energy band? See, this is the acceptor level. We are seeing acceptor level. In this one, electrons and holes are there. So therefore, the acceptors are under the p-type. Now see the energy diagram also one by one. After receiving the electron, the boron atom become negatively ion, but at room temperature provides enough thermal energy to push the electron in the valency band to acceptor energy level. This is the acceptor energy level we are showing. So from boron to conduction band, it results that at room temperature, there are a large number of holes in the valency band compared to the electron in the conduction band. That is, the holes are majority carriers. And if one is majority means another one is minority. So, and electrons are minority. So that the materials are called p-type material. Okay. These are the classification of materials based on the conductivity you are discussing. So basically it is metals and semiconductors, insulators, and once again the materials are further classified into different types, that is intrinsic semiconductor and extrinsic semiconductor. And this what we can say that our extrinsic semiconductor n type and p type, and based on the temperature and based on the doping it is divided. Okay, you can go to complete this class and further we can discuss. Thank you, Ananda. బ్రేక్ అయిపోయింది మధ్యలో ఎక్కడ ఈ రెండే నొక్కుంటా వచ్చిన